Welcome to G Fun Facts Online. Today we are stepping directly into the vibration-isolated clean rooms of 2026 to look at a profound shift occurring in the race for the quantum computer. For decades, the dominant image of a quantum machine was a chandelier of gold and copper. You have likely seen the photos of these dilution refrigerators, designed to cool superconducting circuits to near absolute zero. But as the industry pushes past the 1,000-qubit barrier toward the holy grail of 1 million qubits, a new realization has taken hold. Wires are the enemy. The so-called wiring problem is a fundamental thermodynamic and spatial bottleneck. You simply cannot thread millions of coaxial cables into a cryostat without turning it into an oven or running out of physical space. The solution, which is now driving the roadmaps of major players like PsiQuantum, Qwera, and Xanadu, is to abandon the wire for the photon. This is not merely about using light for communication. It is about a fundamental architectural inversion, where light becomes the structural scaffolding of the computer itself. We are moving from the age of trapping matter to the age of trapping light. In this episode, we are going to delve into the deep physics making the million-qubit era possible, from the nanoscale wavefront engineering of metasurfaces to the quantum optics of fusion measurements. To build a quantum computer with light, you must first master the art of holding it still, or at least confining it long enough to interact with matter. This was once thought impossible because light, by definition, wants to move at the speed of light. However, two distinct physical breakthroughs, optical tweezers and high-Q cavities, have recently converged to solve this. The story begins with Arthur Ashkin at Bell Labs in the 1970s. Ashkin discovered that the momentum of light could exert a physical force. A focused laser beam creates a dipole force, where dielectric particles are drawn toward the region of highest light intensity, much like a moth to a flame, but driven by the gradient of the electric field. For decades, generating these traps required bulky lenses and spatial light modulators. But to scale to 1 million atoms, you cannot rely on 1 million conventional lenses. The breakthrough lies in metasurfaces. A metasurface is a two-dimensional array of sub-wavelength nanostructures, often silicon nanopillars, that act as discrete phase shifters. By varying the diameter and orientation of these nanopillars, engineers can imprint an arbitrary phase profile onto an incoming plane wave. This is wavefront engineering. Instead of a curved glass lens refracting light, the metasurface delays the wavefront at each pixel to constructively interfere at a specific point in space. The scaling factor here is immense. A single metasurface chip can now generate over 100,000 distinct diffraction-limited focal spots from a single high-power laser beam. This replaces the physical wiring of control lines with a hologram of light. The physics here is non-trivial. It requires solving the inverse scattering problem to design a nanopillar map that minimizes crosstalk between adjacent traps, which are often separated by only a few micrometers. This technology essentially acts as an infinite switchboard, overcoming the traditional limits of the space bandwidth product that plagued standard microscope objectives. While tweezers hold the atom in place, optical cavities are designed to hold the light around the atom. This is crucial for readout, which means getting information out of the qubit. In free space, an atom emits a photon in a random direction. Capturing this photon is highly inefficient. The solution is the Purcell effect, a phenomenon where an optical cavity modifies the local density of optical states. By placing an atom inside a cavity with a high-quality factor and small mode volume, you enhance the probability of the atom emitting a photon into the cavity mode significantly. Recent work, such as the Stanford breakthrough in 2026, has demonstrated arrays of silicon photonic crystal cavities that achieve this enhancement for hundreds of atoms simultaneously. The physics relies on slow light modes in the crystal, where the group velocity of light approaches zero, effectively trapping the photon near the atom long enough for a deterministic interaction. This allows for the simultaneous readout of thousands of qubits through a single fiber bundle, completely bypassing the wiring bottleneck. Now, let us look at the matter-light interface. Light is excellent for transport, but poor for memory, because photons do not like to sit still. Therefore, the million-qubit machine is almost always a hybrid, using a matter qubit for memory and a photonic qubit for communication. Companies using neutral atoms like rubidium or ytterbium trapped in optical tweezers are relying on a specific quirk of atomic structure known as erasure conversion to scale. In a typical qubit, an error, such as a bit flip, is a silent killer. You do not know it happened until your calculation fails. However, in atoms like strontium-88 or ytterbium-171, qubits can be encoded in metastable states. The physics here is fascinating. When a high-energy Rydberg state decays, which is a common error source, it often falls into a specific dark ground state that is distinct from the computational 0 and 1 states. The advantage of this is profound. By periodically flashing the array with a probe laser, the system can see which atoms have fluoresced and flag them as erased rather than corrupted. In quantum error correction theory, an erasure error is infinitely easier to fix than a Pauli error because you know exactly where it is. This physics allows neutral atom arrays to function, with much lower fidelity thresholds, accelerating the path to fault tolerance. For ytterbium-171 specifically, the qubit is defined by the nuclear spin states. When the atom decays from the Rydberg state, it often falls into metastable states that are dark to the cooling light but can be detected by a separate erasure laser. This allows a check operation to be run mid-computation, asking if any atom is in the metastable state. If the answer is yes, that qubit is erased, and the logical qubit adapts its error correction code instantly. Another approach involves artificial atoms trapped in the solid state, such as the T-center in silicon. The T-center is a defect complex consisting of two carbon atoms and a hydrogen atom that acts as a spin-photon interface. The defect introduces localized electronic states within the silicon bandgap. Because silicon is the standard material of the semiconductor industry, T-centers can be integrated directly into high-Q cavities. The challenge here is phonon broadening, which refers to vibrations in the silicon lattice shaking the electron levels. Operating these systems requires ensuring that the zero phonon line, the pure optical transition without vibrational noise, dominates the emission spectrum. So how do you compute with 1,000,000 qubits without 1,000,000 control knobs? The answer lies in the architecture of light, specifically fusion-based quantum computing, or FBQC, a radical architecture championed by PsiQuantum. In the standard circuit model used by IBM or Google, you keep qubits alive and apply gates to them. In FBQC, the qubits are photons flying through the system and are destroyed milliseconds after creation. The computation happens in the measurement. The fundamental operation is the fusion measurement. Here, two photons, each from a separate entangled cluster, impinge on a polarizing beam splitter. If the photons are identical in frequency, polarization, and arrival time, a phenomenon called the Hongou-Mandel effect ensures they interfere. Detectors at the output measure the polarization. Because of the quantum interference, certain detection patterns project the remaining photons in the clusters into a new, larger entangled state. This process effectively teleports information and stitches small, entangled resource states created on-chip into a massive, three-dimensional cluster state that spans time and space. The enemy of photonics is loss. If a photon scatters off a rough sidewall in a waveguide, the qubit is gone. However, the stabilizer formalism of error correction shines here. In the FBQC model, a lost photon is just an erasure. Because the three-dimensional cluster state is highly redundant, the system can survive the loss of a significant percentage of its photons. The computation is like a bridge. You can remove random bricks, representing lost photons, and the bridge still stands, provided the hole or erasure is identified. To reach 1,000,000 qubits, you need modularity. You need to connect one chip to another. This is done via entanglement swapping. An ion on chip 1 emits a photon entangled with its spin state, and an ion on chip 2 does the same. These photons meet at a beam splitter in the middle. A Bell state measurement on the photons projects the two ions into an entangled state, even though they never interacted directly. The challenge is that the photons must be indistinguishable. Any frequency shift or polarization rotation destroys the entanglement, requiring frequency conversion crystals to change the photon's color to the telecom band for low-loss transport. Finally, we must discuss the manufacturing limits. The physics of scaling is ultimately the physics of manufacturing. To build a 1,000,000-qubit machine, you need semiconductor foundries to print these optical components. The primary killer of optical coherence is sidewall roughness. When etching a silicon nitride waveguide, the lithography process leaves atomic-scale jaggedness. This roughness causes Rayleigh scattering, which scatters light proportional to the square of the roughness divided by the fourth power of the wavelength. For a quantum computer, even 0.1 decibels per centimeter of loss can be fatal. The fix involves modern photonic Damascene processes and high-temperature hydrogen annealing to reflow the silicon, smoothing these atomic mountains into molehills and reducing scattering to negligible levels. There is also a massive thermal advantage to this approach. Unlike superconducting qubits, which require millikelvin temperatures, photonic qubits operate at warm temperatures of 4 Kelvin or even room temperature for some components. This changes the cooling physics entirely. A dilution refrigerator has microwatts of cooling power at 10 millikelvin. A standard cryocooler has watts of power at 4 Kelvin. This factor of 1,000,000 in cooling capacity is exactly what allows the optical approach to scale. You can pump massive amounts of laser power into the cryostat without boiling the qubits. We are currently in the utility scale transition. PsiQuantum is leveraging standard CMOS manufacturing. Quera and Pascal are scaling their optical tweezer arrays using erasure conversion. Xanadu is pushing the continuous variable approach with squeezed light. The physics of trapping light has moved from a Nobel Prize-winning curiosity to an industrial blueprint. By mastering the interaction of photons with metasurfaces, cavities, and defects, we are finally building a computer that runs not on electricity, but on the fundamental uncertainty of light itself. Thank you for listening to G Fun Facts Online.